Welcome to this video on the global additive manufacturing ecosystem and standards landscape. We will navigate the essential standards, consortia, and qualification frameworks needed for the industrialization of additive manufacturing. In this first section, we provide an overview of the ecosystem and explore why establishing standardized pathways for additive manufacturing is an absolute imperative. Manufacturing is shifting. While traditional methods rely on well-characterized materials and deterministic standards, additive manufacturing introduces unique complexities like anisotropic properties and stochastic defects that defy conventional qualification frameworks. Why do standards matter? They provide a common lexicon for global collaboration, act as a critical tool for risk mitigation, and serve as the foundation for regulatory compliance in sensitive industries. As the scientific consensus suggests, standards are not just guidelines. They are the essential bridge that transforms additive manufacturing from a laboratory novelty into a mature industrial reality. Qualification in AM is complex. It involves managing process sensitivity, addressing anisotropic mechanical properties, navigating intricate thermal histories, and overcoming the limitations of current non-destructive testing methods. The evolution of these standards has been steady. From the formation of ASTM Committee F42 in 2009 and the establishment of ISO TC 261 in 2011, we now have over 100 active joint standards. Moving to part 2 of this video, we will examine the core organizations that are drafting the critical blueprints for industrial additive manufacturing. ASTM International's F42 Committee is central to this effort. Since 2009, they have focused on technical standards for metals and polymers, driving integration into advanced supply chains. ISO Technical Committee 261 maintains a global mandate. It operates through various working groups to cover everything from data formats to safety, ensuring international consensus across more than 170 member nations. The ISO ASTM Joint Framework is powered by a Partner Standards Developing Organization agreement. This collaboration eliminates redundancy through joint groups that harmonize guidelines across the entire AM lifecycle. Beyond general standards, sector-specific bodies like SAE, NASA, and various aviation authorities translate these requirements into official compliance pathways for aerospace and spaceflight hardware. SAE International plays a vital role in mobility. Their AMS-AM committee provides highly prescriptive documents for aerospace and automotive suppliers, ensuring absolute repeatability in manufacturing. NIST, the National Institute of Standards and Technology, drives measurement science. They focus on metrology, in-situ monitoring, and robust data repositories to validate computational models and industry standards. Finally, NASA Standards 3716 and 3717 provide critical requirements for spaceflight hardware, detailing rigorous part classification and process qualification to ensure safety in extreme environments. In the medical sector, the FDA mandates specific focus areas for additive manufacturing. Key requirements include a rigorous biocompatibility testing of materials, ensuring structures can be effectively cleaned and sterilized, and managing the unique challenges of patient-matched anatomical devices. The industry's growth is reflected in the scale of standardization. With over 100 active joint ISO and ASTM standards, the landscape is rapidly maturing, covering everything from fundamental powder rheology to advanced post-processing techniques like hot isostatic pressing. We will now deconstruct the additive manufacturing standards framework by categorizing them. These categories provide structure to the expansive list of technical documents governing the field. The first two categories are terminology and design. Terminology establishes a universal vocabulary to prevent miscommunications, while design guidelines focus on design for additive manufacturing, or DFAM, including topology optimization and digital product definitions. Statistical material qualification is another pillar. For B-basis allowables, standards define how to calculate tolerance intervals to ensure high survival rates with statistical confidence, compensating for the inherent process scatter found in additive systems. Categories 3 and 4 cover materials and processes. Material standards govern feedstock characterization, while process standards dictate strict machine parameters and environmental controls to ensure consistent and repeatable energy delivery. The digital thread acts as the connective tissue for these categories. It ensures seamless data provenance from the initial design through material tracking, machine logs, and final inspection, while increasingly addressing vital cybersecurity requirements. Feedstock characterization is crucial. Standards regulate powder flow properties to prevent mechanical failures and establish strict recycling protocols to manage the chemical degradation of materials over repeated build cycles. Process control standards are equally vital. These include freezing parameters after qualification, requiring mandatory stress relief heat treatments, and maintaining immutable machine logs of anomalies for future root cause analysis. The fifth category involves testing methodologies. These standards provide the consistent, standardized approaches needed to verify parts and materials across different additive manufacturing platforms. Global adoption of these standards varies by sector. Aerospace and medical industries have led the way due to strict regulatory requirements, but other sectors are rapidly adopting these frameworks as additive manufacturing scales. In the final part of our video, we will examine several foundational ISO and ASTM documents that serve as the bedrock of the current additive manufacturing landscape. ISO ASTM 52900 is the universal dictionary of the industry. It defines the 7 core process categories of additive manufacturing, providing the legal and contractual clarity necessary for global business and intellectual property. ISO ASTM 52910 outlines the general framework for design. It provides process-agnostic guidance to help engineers identify opportunities for part consolidation, lightweighting, and early-stage cost evaluation. Finally, ISO ASTM 52911 focuses specifically on powder bed fusion. It details technical design constraints like managing support structures, evacuating trapped powder, and minimizing thermal warpage to ensure high-quality, repeatable outputs. Next, we look at ISO ASTM 52921, which defines coordinate systems. This standard is essential for standardizing the orientation of parts within the build volume, ensuring uniformity relative to machine architecture. This standard is critical because additive parts are anisotropic. By specifying the Z direction consistently, manufacturers can ensure structural integrity and predictable mechanical performance in their final components. The implementation workflow for these standards follows a 3-step process: formal specification, controlled manufacturing execution, and rigorous verification through testing and documentation. When dealing with metal powders, safety is paramount. ISO ASTM 52931 provides the necessary protocols to mitigate risks related to inhalation hazards, combustibility, and proper hazardous waste disposal. This joint framework is powerful. As industry leaders note, it successfully harmonizes the digital definition of a product with its final physical manifestation, which is essential for industrial-scale manufacturing. Now, we explore qualification and certification, the final hurdles to achieving airworthiness and securing regulatory approval for high-consequence parts. While often conflated, they are distinct processes. Qualification is the internal, data-driven validation that a process consistently meets specifications. Certification is the formal legal endorsement granted by regulatory authorities like the FAA or EASA. For aerospace engines, the FAA's Part 33 governs airworthiness. It requires demonstrating that additive parts are equivalent or superior to legacy counterparts in extreme fatigue and thermal environments. 2 key strategies define the certification of these parts: the point design approach, which treats a specific machine and geometry as an indivisible system, and the shift toward generalized statistical databases. To achieve compliance, companies must submit a detailed plan, conduct extensive coupon testing for baseline properties, and perform full-scale engine block testing to simulate real-world service conditions. The aerospace certification pathway is a 4-phase journey, starting with machine qualification, moving to material and process development, transitioning to component-level inspection, and concluding with final system regulatory sign-off. However, entering this space requires overcoming significant hurdles. It typically demands 3 to 5 years of dedicated R&D and millions of dollars in capital investment to prove reliability. Mitigating process variation remains a constant challenge. Consequently, standards often mandate post-processing steps like hot isostatic pressing to ensure consistent microstructure and eliminate internal porosity in flight-critical parts. To succeed, many organizations rely on industrial alliances. These research institutes, user groups, and public-private partnerships accelerate technology transfer and share best practices across the global manufacturing landscape. A prime example is America Makes, the National Additive Manufacturing Innovation Institute. They coordinate R&D funding, support foundational standards development, and drive the overall maturation of the domestic supply chain.